gonna do today. All right. So last week, Alice has already gone through unsupervised learning, those really old algorithms. So today we're actually gonna talk about supervised learning, and with this short introduction, we're trying to cover these concepts, right? Loss function, and how we can minimize the loss function using gradient descent, and how we perform gradient descent using chain rule. Okay. And then after this short introduction, we'll do a bit of linear regression. So we'll talk about how the learning algorithm for linear regression works. We're going to talk about the different types of gradient descent. We're going to briefly touch on the bias variance trade-off. We're going to talk about regularization for linear regression. And then after that, we'll talk about some TensorFlow stuff. And if we finish on time, then I'll give you guys something to do related to linear regression. Yeah, okay. So let me just change the window to here. Okay, y'all can see the thing.
Yeah, no problem.
Okay. Okay, all right. Okay, so let's see. Introduction to supervised learning. So in general, in supervised learning, we're working with sets of training sets. So okay, let me just use white for this. So we're working with training sets, right? Training sets, and training sets can be expressed mathematically as a set, right? So let's call it S, and it has a number of samples there, and you can express it like this. So it's usually a training sample. One sample is consisted of some input features, which is a vector, right? And its corresponding labels, which is also like stored in a vector, right? And because we have n samples, so our I here can be from 1 to n. Okay. So usually work with these training sets. And these features and labels, they can be um, arrays of like any dimension d, right? So they can be two-dimensional, they can be one-dimensional, they can be really high dimensional, right? So for the purpose of the discussion of this short introduction to supervised learning, we're going to say that our input feature we're working with is 1D, right? So x will look something like this, right? Is So x might look something like this. You have 1, you have 2, and so on, right? Okay. So let's begin by plotting. Let's begin by plotting how a point will look like, how x and y could look like on the axes. So okay, this is pretty big. Okay, just maybe something like this. Let me copy this. Okay. So we have x-axis and y-axis, and let's just say we have some arbitrary points, and we plot it on this axis, so it could look something like this. So in a supervised learning context, there are like two main things that we want to do with a sample space like this. So the first thing we can do is to predict the y given certain x, right? So to model the relationship between x and y. And in this case, this can be a really simple linear relationship. So you can just draw a best fit line that looks something like that. Or it can be very complicated. It can be as complex as you want. It can be like a polynomial with very high degree. So you could like look something like this, right? So yeah, basically model the relationship between x and y. That's the first case. The second case that we are concerned with is classification. All right. So instead of for classification, instead of drawing these best fit lines, you'll be drawing these things called decision boundaries, and they can be linear again, like a single line like this. So everything here is one class, and everything on the other side is another class. Or it can be again non-linear, so it can be something like a curve like this, and everything here is a class, and everything on the other side is another class. And as you expand the dimensions of your x from one dimension to two dimensions, three dimensions, so on, your decision boundary transitions from lines to planes to hyperplane. Okay, so all these are generalizable to multiple dimensions. So for the sake of the introduction, we're just mainly going to concern ourselves with the prediction, the modeling of relationship between your input and output. So let's go ahead and do that. I'm gonna paste the axes again. Okay. So again, we have x and y, and we have some points like this. Yeah, okay. And let's consider a very simple case where we want to try to predict a model a linear relationship between x and y. So again, you draw the best fit line, okay, and this best fit line will be our model for this data set, and we can express this model very easily in mathematical notations. We can call it y hat, and y hat is equal to certain theta 1 multiplied by x, which is your input, plus a certain offset, we call it theta 2. So this is just your mx plus c formula, right? So you guys should be familiar with this. And to improve how accurately this model is able to fit our data, we have to introduce the concept of the empirical risk, or a loss, right? And for such a naive case, or such a simple case, we have many different ways of defining what the loss is. And in this case, I'm just going to define loss as, let's say, the absolute distance, let's call it d, between a true label, which is y, and a predicted label, y hat, right? So the absolute distance between the 2 points. And again, we can express this mathematically. So we can do L, which is our loss function. It has inputs x, and the ground truth label is y for training, and has certain tunable parameters theta. And theta is consisted of your theta 1 and theta 2, right? And you can write because again x and y are vectors, or arrays. Yeah, it consists of many elements. You sort of have to sum over them. So 1 over n is to take the mean of the loss from let's use I, from I equals to 1 to n, and you can calculate absolute distance for each of these i's, right? So it'll be a y hat I minus y, and your y hat comes from this operation which uses x, right? So with that, we have introduced the concept of empirical risk, and the loss. So, and our goal here to improve this algorithm is pretty clear: to minimize your L, minimize your loss, right? That's our goal. Okay, wait, is someone wait, Shashan, are you like leaving and joining? Are you having problems?
No.
Okay, then I keep hearing someone leaving and joining who's having problems. No one's having problems. Okay, then I just continue. All right. So again, you want to minimize L. In this case, our L is defined like this, right? And before we move on to talk about how we can minimize L and improve the accuracy of our model, I'm just going to briefly introduce the concept of a nonlinearity. Okay, let's nonlinearity. Okay, so nonlinearity is basically like a function, a mathematical function that we apply onto the output of your model. So in this case, we apply this on the y hat, which is like a single neuron, if you would like. We apply this activation onto the output here, and there are many different types of activation functions you can use, and generally they're denoted as sigma, and they take in the output of a single neuron. In this case, it's y hat. So in this case, I want to introduce you guys to a very basic activation function, which is called sigmoid, and it can be expressed in this format, right? This, and if you are to plot the graph of a sigmoid function, you have, okay, let's call this z, right, for simplicity's sake, because I don't have to keep writing this again. So z, and then this is your input. It will look something a little bit like this. Okay, so you're gonna have a asymptote here and a asymptote here. This asymptote here is 1, and this is half, and sec is half, and it goes 0. So it basically squashes value here. And this is just one of those nonlinear functions that you apply onto the output of neurons. And for now, you don't really have to know what they're doing. I just want to introduce this so that you guys know that it exists, and we often use this in machine learning. Okay. So with this introduced, we can move on to talk about how we can minimize our loss, right? And to minimize the loss, we have to use something called gradient descent. And let's just write down here gradient descent. And for gradient descent, it's most intuitive to explain this concept if we are to plot, again, a graph. Actually, let me just copy the X. If we are to plot the graph of how the loss looks like with regards to one of these tunable parameters. We have theta 1 and with theta 2. So in this case, let's just concern ourselves with theta 1. if we can do the we can if we can perform gradient descent for theta one, we can also do the same thing for theta two. So we plot the loss value with regards to our theta one, and let's just draw an arbitrary looking curve. Maybe it will look something like this. All right. So our goal again is to minimize L. So in this case, it's pretty obvious that the minimum point is somewhere here. That's our global minima. And you'll notice that in places there can be local minima. So there's like these small dips which are local minimas. And yeah, those are not our goal. Our goal is to globally minimize L, right? So let's say we are a point somewhere here, and currently we have a certain theta value, just call it theta, and the steps towards moving from this point to the global minima first starts with the gradient, right? We calculate the gradient at our current position. So this gradient would just be tangent tangent to our current position of the slope. So this is the gradient. And once we know the gradient at our current position, we can take a step in the opposite direction of this positive gradient. So because if the gradient is positive, we want to go in the opposite direction to go down the slope, right? If your gradient, however, is on this side and it's like negative, then you can just move your point to the right instead. Okay, so you want to take into account this gradient, and we move a little bit, just nudge this current point a little bit to the left, and then that will give us a new value, right? This new value here, which is closer to the global minima, we can call this new value theta hat, right? So with that really hand wavy introduction to the gradient descent, we can now move on to how we can mathematically represent this set of operations. Now, for theta hat, we can express it as theta, which is this value here, minus away uh, the gradient, right? So the gradient we can express as this upside down triangle with respect to theta one of the loss function, which again has inputs x and y and parameters theta, right? And because the gradient only really tells us where we are going to move, right? If it's a positive gradient, we'll move to the left. If it's a negative gradient, we'll move to the right. It will tell us where to move, but it doesn't tell us exactly how much to move. So we need an extra parameter here called eta, and eta is your learning rate. And this learning rate essentially determines how long this little arrow here is. If it's a really large learning rate, your arrow will be bigger. You take a bigger step each time. If your learning rate is smaller, the arrow will be smaller, and you'll move a little bit less each time. Okay. So how do we obtain the expression for the gradient of the loss with respect to your theta, right? And with that, we have to sort of perform chain rule, and you guys should be familiar with chain rule. It should be taught in secondary school, right? For your calculus stuff. So let's just briefly revise how we will obtain the expression for this, right? So we want to find the gradient of L with respect to theta 1. And for reference, I'm just going to copy the L here. So our L was defined as this little summation. Okay, it starts from 1, goes to n. So that, yeah. And let's just take into account the activation function as well. So our z is equals to 1 over 1 plus e to the power this. All right, let's take into account this as well. So to find this is essentially taking dl with respect to the output of this the activation function, and taking dz with respect to the output of your neuron, which is theta dy hat, and then dy hat d theta, right? So this is your chain rule, right? You notice everything cancel out and give you dl d theta. So that's your chain rule, and we can do this step by step, right? So we can first differentiate our loss function with respect to z. So this in this case will be z, right? So if you just differentiate z because it's a linear function, you'll get something like 1 over n equals 1 and inside is just 1. And you'll differentiate uh, z with respect to y hat. So multiply dz dy hat. These are within the summation, and dy hat with respect to theta 1. Theta 1. Okay, let me zoom in a bit. And we can proceed with differentiating this. So copy this. And okay, if you differentiate this, you'll get firstly -1, you move it out, plus e to the power of that, and this is to the power of 2 now, and you'll differentiate the inside, which will give you negative negative of e theta, right? Is that correct? Oh, this is negative, and you'll multiply by this again. Okay, and these are all within the summation, and you can just rearrange this a little bit. And this is actually a really easy differentiation because this is a linear function. Y hat is just, if you differentiate with respect to theta 1, it will just give you x, right? So we can just put it in as well. Okay, wait, let me just, okay, that one cancels out. So actually I should be writing I here, but never mind. And you'll multiply this by this, and you'll divide by this, right? So this essentially is your gradient, right? Yeah. And you'll notice this summation, and this is basically taking the average of the gradient contributed by each sample. With respect to every single data point in your entire sample. Okay. And we can perform the same set of operations because again we have theta 1 and theta 2. We can perform the exact same set of operations for theta 2. And you'll realize that the expression is very similar. It will just be without this x. Just be like this. And you can take a step for each of these two variables for each of the learning cycles, right? And that's just a really quick mathematical derivation of how we can arrive at your gradient. Okay, and now let's talk about this new variable that we just introduced, which is called eta, the learning rate. Let's consider how. So again, we have, let's just plot the graphs of your learning rate, your loss with respect to say theta 1. Let's consider two cases. One case where you have a really high learning rate, and one case where you have a really low learning rate. Okay, so let's have a similar graph, some local minima, something like that. Okay, and again, let's say our point is here, and our goal is here. If you have a really high learning rate, you realize that each step you take will be really big. So what might happen from this point is, instead of taking this nice little step here and then go down the gradient, you might be taking a really, really, really huge step, and that will cause your point to end up somewhere here across the valley. And then from here, you want to go to the right, so maybe you'll take a point, like take a step to somewhere here, and then you'll keep bouncing around this valley without actually touching the minima. And sometimes you can even go out of this zone here, right? So it'd just be really unstable. You'll be bouncing around a lot. But one thing is that if your current point is somewhere here and you're taking really large steps, then you have a chance of getting out of this little hole here and actually go to the global minima. Right? So that's one thing to take note with a high learning rate. And you have a really low learning rate on the other hand, what happens is that your convergence will be much smoother, right? If your point is starting from here and then you'll go smoothly down the slope very slowly, and then eventually settle somewhere here, maybe oscillate a little bit, but not too much. So that would be really smooth. But if you are here and you're having a really small learning rate, what will happen is that you'll take these really small steps down to the local minima here, and your model will essentially be stuck here, and it won't be achieving the global minima of the loss function. So there needs to be a balance between a high learning rate and low learning rate, so that it's high enough for you to sometimes bounce out of these situations, but also not too high that you will be going past your global minima a lot. Which is why in some training schemes, you'll see that they start out with a pretty high learning rate, and as training goes on, you'll see that they tune the learning rate down so that the convergence can be smoother. Okay, so that is about all I want to say for the introduction to supervised learning. And actually, we didn't take too much time. So, does anyone have any question? If there are no questions, we will like move on to linear regression. Any questions for now?
Uh, Ikin,
Yeah.
yeah, can I ask like what does like the optimizer do?
The optimizer, so it controls is basically like a way for you to control how the steps are taken and how the learning rate changes sometimes. Yeah. And also the later you'll see that when we introduce the concept of regularization, actually optimizers have something to do with regularizing your training process as well. Yeah. But those are concepts that we're not touching today for now. Yeah.
What does A in the loss function represent?
The A in the loss function where let's go back. This where
Oh wait, that's a theta.
yeah, that's a theta. Yeah. So these are your tunable parameters, which is theta one, theta two. Right.
All right, thanks.
I want to ask something.
Okay.
I think in some loss function they take the main square thingy, whereas
Oh
here
yeah.
you just take the
We'll talk about that later. So right now we
okay,
just consider a really naive case for simplicity's sake.
okay, sure.
Yeah.
But is there a like subtle difference or
We'll talk about the mean square error in a bit. Of
okay,
course, it's
sure.
different. Yeah. Yeah. Of course, it's different. So, any other questions? Okay. If there are no questions, then I'll start with uh, linear regression. Let me clear all these. Okay.
Wait, sorry. Just now I was lagging a bit. How does the loss?
And I think Alice will send you like
Oh God.
all these stuff later, or I will send you all these stuff later. So, uh, if you need to, how does that? Again? Hello?
Yeah. So how does the like loss function relate to the activation function? Like because you
For a
need
moment.
because sorry, I think I'm lagging a lot. Like how do the loss function and activation function relate?
Are you still there?
he asked how does activation function and loss function relate? I can hear him, but like yeah, I mean it's either I'm laggy or you're laggy.
It's not laggy. I think it's just him.
Yeah, hello? Okay, I think I have a problem. Okay. Wait, so what was the question again? What was the question again?
Yeah, he asked how does loss function relate to optimization? Is it optimization function, something like that?
How does relate to the loss activation function relate to the loss function? Okay. So in a typical scenario, like when you're doing neural networks, what will happen is that your single neuron can be the y hat function that we just illustrated, right? You have a theta one, this, and usually this does not directly go on to the next layer. Instead, it will go through an activation function, and the output of this activation function will go to the next layer. So in a single neuron model, what will happen is that the loss function is not computed on just this alone. The loss function is computed on theta y hat, right? So instead of your loss function being just an absolute difference between these two, it will be the sum of the absolute distance between z minus y, right? So that is why when we take gradient descent, you have to take into account the activation function, because they are all part of the process in obtaining this final output, and as a result in the loss computation. So you have to take into account all of them. Yeah. Is that clear? Am I lagging or is oh, okay, all right. So we can finally move on to linear regression. Everyone's fine, right? Okay, I'll take that as a yes. Okay. Let's talk about linear regression. So just now we have considered a really simple case, which is also like a regression case, but really specific case where your feature inputs are like one-dimensional. So in regression, we'll again be working with our training sets. So let's call it Sn again, and there'll be still pairs of values.
Wait, Yiqing, I think I can't see your screen. Oh, yeah, I can already. Okay, sure.
And it'll still be pairs of values. But in this case, your x can be any dimension. It doesn't have to be one dimensional. It can be any dimension, right? So again, yeah, you can. Okay, all right. So again, it can be your input feature. Wait, can you all hear? Okay, wait. Are you able to hear me?
Yeah.
Okay, all right. Okay.
Yeah.
Some internet problems. All right. Okay. So I'll move on. Okay. So because we already went through all these things about training algorithms and linear gradient descent and so on, we can just move quickly through this part. So you will have because just now we only consider a one-dimensional case, our theta will have be slightly modified, because theta now is also the same dimension as x, right? Because for each dimension of the x, you have to have its own theta, right? So we can express our model still in the same fashion, but a little bit more generalized. So you have input x, and you will have this set of parameters theta, and you have offset, right? And this will be the sum of, okay, from I equals 1 to dimension. Okay, let's use t actually. T equals 1 to the however many dimensions your input features have of theta, which is your weight, multiplied by x t, and plus the offset, right? So in this case, your x here is just one single sample. Okay, so your multiply, you basically do a element wise multiplication between the weights and the inputs, and you add this offset after all that, right? And you can just compress this expression into just theta multiply actually dot onto x plus the offset, right? So your shows, I think yours should know what dot product does. So if your q is something like 1 and 2, and your x is something like 2 and 2, and if you dot this 2 together, it will just be 2 plus 4, 6, right? So this is what it's doing. It's basically element-wise multiplication, and you sum everything together. Yeah. Okay, so that is, for the general case, it's still the same mx plus c equation. Now, moving on, the next step is to again define the loss so we can actually improve the algorithm. Okay, so let's do loss. So again, just now in that really simple introductory case, we only consider the absolute distance between the input and the labels. So in this case, we're gonna use something that's a little bit more elaborate. So we're gonna have a loss function r, which is based on n samples, and this parameter theta is equal to still a very similar form. Okay, I'm gonna do a half outside here. Okay, and it goes from I think we're doing in I, right? Yeah, we're doing in I, so we're gonna start from I equals 1 to n, and in this case we're using the mean square error. So you'll take your that whatever function, we can just call it y hat minus. Oh, actually, let's take y, which is your labels, minus the theta multiplied by xi, you square it, right? So this is the, without a half, it's just a normal mean square error, and I'm having a half here so that when we differentiate later, this 2 will cancel out this half, so we don't have to worry about it. Okay, so this is your standard mean square error, which is used pretty often in many machine learning models, right? So now with our loss defined, we can again move on to performing gradient descent. Okay, so just now we considered the gradient for the entirety of the loss function, so that included the summation here. But in this case, let's consider something different. Let's just consider the gradient with respect to theta of. Oh yeah, actually, I forgot to say something. When we do these derivations, let's just assume that, let's just ignore the theta naught in this case. So let's say theta naught is equal to 0, so we can ignore this completely here. Because again, if we are able to do it for this, we can do it the same way for this. So we're just gonna not care about this for now, so we can do this a little bit more cleanly. So we find a gradient of this function just with respect to theta, right? Okay, let's just write y minus. Okay. We have our half here. So this half can be moved in and out of the summation, doesn't really matter. So instead of finding the gradient of this entire loss with the summation, we just find the gradient of this one loss, right? So if you differentiate this, you'll realize that this is just negative of y minus your theta, right? So it's negative because when you differentiate the inside, you get negative x, actually. Yeah, when you differentiate the inside, you'll get the negative x out. So with this, we can express our step. Your theta hat equals your old theta minus away this, so it becomes plus, and multiplied by your learning rate. Okay, so notice that the form of our step is a little bit different from what we had just now, because just now we had this summation and your function inside. So we're taking the average of the gradient. So, but in this case, we're apparently performing a update to our theta based on just one sample, right? Based on just one sample. So this is what we call stochastic gradient descent, in which the updates to your tunable parameters are based on just one sample. Okay, and there are multiple different types of gradient descent. Again, we have the batch gradient descent, which is what we actually did during the introduction. That's batch gradient descent, where we take into account every single sample in your training set and take one step, right? So if let's say our n is equals to 5,000, right? For stochastic gradient descent, you'll take 5,000 steps. But for batch gradient descent, based on this 5,000 samples, you'll take one step, right? All of these samples accumulate into just one average step. And there's another type of gradient descent called mini batch gradient descent, which you will take a subset of your n samples and you take one step based on that. So it's something called batch size. So based on your batch size, your steps will be computed based on the average gradient of one batch of samples, right? So let's discuss more about these different types of gradient descent. Let's start with talking about the advantages and disadvantages of using stochastic gradient descent. People usually call this SGD. Okay, actually use a different color, SGD. So let's talk about the advantage of using this. Right, there's some advantages associated with SGD. So the first very very obvious benefit of doing SGD is because you're only performing gradient descent on a single sample. It will definitely fit in your computer's memory, right? Unless you're doing some freakishly large operation with some really high dimensional image, it's very unlikely that when you're doing stochastic gradient descent, your data won't fit in the memory, right? So you'll definitely always be able to perform that gradient descent. And second thing is that it's really fast to compute, because again, you're doing just one set of operations based on that one sample, right? And three is that because you're updating, let's draw like a top down view of your loss graph. Let's say it's just 3D one. So it's like then you have a certain like a gradient looking thing. So you remember your geography stuff. When you have these rings, it means like it's going up or going down. Let's say this is the basing, and then you're somewhere here, you want to go down to the basing. What happens with SGD is that you're taking these steps which are based on a single sample, right? So your step can be really kind of random. It can be very zigzaggy, right? You'll not be like going exactly in the direction of the downward slope. You might be zigzagging down this slope and eventually get there, right? And again, because you have these random steps, if there is like some sort of like a small dip here, like a local minima, it's very easy for you to get out of these local minimas. So it's very similar to that analysis we made based on a really large learning rate. Having stochastic gradient descent is similar to that. You can get out of these local minima due to these random steps, which are contributed by single samples, right? These are some advantages. Now let's talk about some disadvantages. So the first thing, again, it has to do with the zigzagging movement. Although these kind of random steps helps us get out of the local minima, it will cause you to have slow convergence, because you're taking all these traveling all these unnecessary distance to get to the minima, which makes your training process entirely slower. And another thing is that even after you have gotten to the minima, you'll be oscillating about the minima. Right, so it's not exactly clear if your model has converged. It'll just be oscillating there, which is not exactly something that's desirable. And the third thing is that although just running on one sample is quite fast, you have to do this for n samples, right? So every single training loop you do can be very very slow, because you have to go through all these set of operations to get that gradient for every single sample. So if your sample size is like 500,000, you have to compute these set of operations 500,000 times, and that would be quite slow for each training loop. And another thing is that although it's pretty fast to compute just one sample, it's actually not very computationally efficient. Right? So when working with machine learning, what you want to do is to compute stuff in batches so you can vectorize them and just perform vector dot products or matrix multiplication, which are generally more efficient and makes use of your hardware more than just computing a single sample like that. Okay, so these are some advantages, disadvantages of stochastic gradient descent. Let's talk about then the next thing, which is batch gradient descent. Okay, batch GD. Okay, we start with the advantages again. So, very similar to our discussion regarding that a very low learning rate. This will help you to have smooth convergence, right? Because when you're taking the average of the gradient contributions of all your samples, it's more likely that the gradient will be moving towards directly the minima, right? Instead of doing that zigzaggy movement. And because of this, you also have less oscillation. So again, smooth convergence. And because you're now performing stuff on batches, you can vectorize it. Right, which is more computationally efficient than performing operations on single samples. Right? These are some advantages. And for disadvantages, one very obvious is that if your sample size is really large, if your n is 500,000 and you're training on images and stuff like that, might not fit in your memory, right? Your data set. Because for batch gradient descent, you have to compute the average gradient for all of the samples, not just a batch of it. So if your training set is really large or the data is really large, then it might not fit in your memory and you can't really perform operations. And which is again similar to the analysis of a small learning rate. You can get stuck in local minimas, right? Because your steps are so ordered and so smooth and go in a single direction, it's very unlikely for you to get out of a minimum point. And the last thing, which is also quite obvious, is that training takes really long. Training epochs takes very long, right? Because again, you have to perform all these computations for all these samples. So that brings us to a mini batch gradient descent. Right, which is sort of like a compromise between the two, and most frequently used in the industries. Right, so like whenever you implement something, you almost always use mini batch gradient descent. So the advantages, I only have advantages for mini batch gradient descent. So firstly, it is you can adjust the batch size, because batch size is another one of those variables. It will definitely fit in memory. Right, if worst comes to worst, you will be performing gradient descent on a single data sample, which is going back to SGD, right? So it will definitely fit in memory. You can always tune that, and still is vectorizable because you're still doing stuff in batches. And three is because again you're not your batch size is very likely to be much smaller than your entire data set. So for example, you have a data set of n equals 500,000. You might be taking batches of 256 samples or 64 samples, which is a very much smaller than the entire batch, entire data sample space you have. So you'll be taking some random steps, right? And these random steps can get you out of local minimas. But at the same time, although you're taking these random steps, they're not that random, right? They're not based on just one single data sample. So you can still have a relatively smooth convergence, a very smooth training process. And your entire gradient computation will be quite stable, right? So basically, through analysis of these different types of gradient descent methods, it's pretty obvious that you almost always want to use mini batch gradient descent. Okay. And actually, that's about it that I want to talk about for these gradient descent methods. Moving on, let's talk about another thing, which is like one of the central problems of machine learning, which is the bias variance trade-off. Let's use a different color. Okay, so to talk about this, we have to first sort of define what bias and variance can be. So in machine learning, your bias is actually sort of referring to when your model is unable to does not approximate your training samples. Does not do it very well, or in other words, your model is really inflexible, right? And this generally translates to the issue of underfitting. So to illustrate this, let's have some plots. Okay, I should still have that. Yeah, let's have some plots here. Let's say we have your labels and your x, and you have some line that doesn't exactly look linear, and you try to fit like a linear relationship between x and y. This is having high bias because this linear line is not flexible enough for you to fit onto this data trend. It's like you trying to fit that straight line curve onto that whatever data set you collected in science practical, but the data set looks exponential, and you sort of have just make do with this, right? So that's the bias issue. Let's draw small. Okay, so that's bias. The other thing on the other end is problem with variance, right? And this occurs when your model is affected by like every little noise and every little feature in your training sample. So in other words, it's a little bit too flexible or a little bit too complicated for whatever data set you're working on. So this all generally translates to the problem of overfitting. Okay, so to illustrate this, let's say we have another plot here, and then let's have some data points. Okay, so this is very obvious, like a linear relationship. But if you have a really complicated model, some high degree polynomial model, instead what it might want to do is, let's say your training sample is, let's put some test samples actually. Let's say you have some test samples. These are test samples, and you train on the white dots. What might happen with a really complicated model is that it will try to fit exactly onto where your training points are, and when you'll notice that when you actually perform, you're not actually going to predict any of the test points correctly, right? So it fits too well onto your training set, and that is the problem with a high variance. So generally, you want to balance the choosing of the model, the complexity of your model. You don't want to be too simple to try to fit a linear line on an exponential graph. You don't want to be too complicated to try to fit some high degree polynomial curve on a linear trend. So you want to compromise between the complexity based on the sort of data set you're working with. And this sometimes you have to do it like in a trial and error manner. And this also explains why when you train a really large model, a really complicated model with many layers on some data set, it might not necessarily perform better than say a simpler model. Sometimes it might even perform worse, right? So always take into account the problem of bias and variance when you consider what kind of model to use for training. Okay, then with that, there is one last thing I want to talk about for linear regression, which is regularization. Okay, so the central goal of having regularization pertains to the goal of machine learning algorithms to generalize, right? So when you train your machine learning model on the training set, your hope is not for the model to perform extremely well on the training set, but rather to have that performance translated to real life applications. So to have a good score on the test set, and as a result, be able to be applied in the real world, right? So generalization. And the generalizability of your model is sort of affected by the quality of the data set and the size of the data set. So what I mean by quality, if your data set is really noisy and it contains like these sort of mistakes, and your model is trained on a data set of a lot of these noise and mistakes, it's very likely for your model to learn, pick up those mistakes and think that they're correct. And as a result of that, of a skewed data set that you train on, when you apply a model to the test set, it might not perform very well. And similarly, if you have a really small data set and it's consisted of specific features, when you train a model on that and you try to apply it onto more general cases, it might not have enough information on those features, or it might be too fitted onto these features that's present within your small data set to perform well, to generalize well on a test set, right? So how regularization help is that uh, it tends to push your weights, which is your theta, towards zero. Try to minimize the magnitude of your weights. So let's just quickly express this in terms of math with a new loss definition. All right. So let's call a new loss function L, which has n sample and is based on a new sort of parameter called theta, called lambda, and still operates on theta. So this new loss function with regularization is the same old loss function with a new extra term, and the term is as follows. You have a lambda, which is the parameter you can choose, and the square of this. So this actually means the norm of your vector here. So let's say your theta looks something like 1.2 and 2.2, and if you do this, you're actually just finding the magnitude. So it's essentially 1.2 squared plus 2.2 squared, which is something like 2.51. Right. So this operation is finding the magnitude of your weights vector, right? And you square that. Okay. So you'll notice that because now this term is in your loss term, and our ultimate goal is to minimize this term, then your model will also have to minimize this term, which is why it's pushing your weights towards zero. Okay. So why do you want to do this, right? The basic concept behind this is that unless there's a really, really good reason for you to pick up certain features and move your weights towards non-zero values, there's really no reason for you to pick up those features, right? So that will prevent your model from picking up the noise in your data set, which is not necessarily important, and only focus on the more important general features. Okay. So, and lambda is a parameter that you choose that determines how strong this push towards zero is. Right, so you have a really large lambda, then your model will always try to minimize the weight and push it towards 0. If you have a relatively small lambda, then it will have less of a regularization effect. Now let's also derive this the gradient of this new loss function. So gradient with respect to theta. We find, so this is just finding the gradient of this thing plus 2 lambda theta. Okay, so actually here's a little bit of a rule with when you operate with vectors. So the derivative of this is actually just this. Okay, this is one of the rules. And if you just copy over whatever we had just now, so this is still that single variable, not the one with the summation. You'll get, okay, there's no 2 here because we had a half. And you can actually append a half here, so it will cancel out this, so you don't have to worry about that. Look something like that. And each of your step will be theta minus your learning rate multiplied by 0. Oh, there's no this. Okay. Right, yeah. And we can sort of simplify this a little bit. Theta, theta. Okay, yeah, that's correct. And this theta can be moved out, yep. Plus your this. Right, okay. So you'll see that from this term, your weights are indeed getting smaller, as long as this is non-negative, right? So far so good. We have covered the concept of regularization. We can briefly take a look at how your weights look like depending on how strong this regularizing factor is. All right, so we have do axes here, and let's say this is frequency, or maybe something like number, and then this is the value of your weights. And if you have a let's say like a large lambda, then what you will realize is that the distribution of weights tends towards 0. You have like a peak at 0. This is 0, and you'll look at something like this. And you have if you have a relatively small lambda, on the other hand, you'll realize that your weights will be distributed a little bit more evenly with a little hump here. Okay, so it'll be generally unaffected. And yeah, that's about all I want to cover. This is actually called L2 regularization. There's also L1 regularization, but you can look it up yourself. And actually, there's one thing I want to touch on, which is regards to loss. So you realize that this square term here. So firstly, this square term ensures that there's no negative values, so that the positive and the negative values doesn't cancel each other out. Another thing is that because this is squared, we are actually penalizing the model more if it's more inaccurate, which is desirable because if it's very inaccurate, then you definitely want it to learn more. But if it's relatively accurate, the square of the value will be smaller. Then it doesn't matter as much if you keep trying to improve in that situation. Okay, so that's why there's a square there. And this is obviously different from the absolute error that we talked about just now, right? And yeah, actually that's about it for linear regression. And again, this is generalizable to feature inputs of any dimension as long as you declared the weights correctly. Okay, so is there any question?
Can we zoom into the regularization again. I am a bit lost. Like,
Okay.
what's the purpose of pushing theta towards 0?
Mm-mm. So by trying to minimize your theta is essentially like a regularization force that try to keep your model unaffected unless there's a really good reason for the model to be affected, right? So if you without this regularizing force, whatever little feature, depending on the complexity of your model, whatever little feature, little quirks that you have in the data set will have an effect on the loss, right? But let's say your loss is not going down once you add this regularization term, then we know that the whatever little feature is contributing is not it's not worth learning, right? Because it won't contribute enough to the optimization efforts in comparison to the magnitude of the weights. So essentially, it's preventing your model from picking up very specific little features that does not necessarily have a very significant contribution to the loss minimization process. And yeah, that's essentially what it's doing. You just have to know that it's a way for you to prevent your model from picking up noise in the dataset.
The y-axis of that graph that looked like a normal distribution. Yeah. What does it say?
Oh, it's basically the number of weights that has this value, right? So if you have a really large regularization effort, then more of your weights will be at 0, right? Just consider a model with many, many weights, of course. So that you'll get a distribution like this. So generally, you might expect your model's weights to be more like evenly distributed across all the spectrum. Yeah.
Wait, so larger regularization term causes weight values to.
Yeah, because having a really large lambda means that you really now want to minimize this term, right? Because it's in the loss, you want to minimize the loss. And to minimize this term, you can't change lambda. The only thing you can change is the magnitude of your weights.
Okay, thanks.
And just one question for you guys to think about. If you have, let's see, let me just quickly do this. If you have like something like a data distribution that looks like this, have x and y. Let's say now we set your lambda equal to infinity. What would be the model? What the model look like if your lambda is infinity? Yeah, let's say your model is like some linear model, some offset. Yeah, let's set your lambda to infinity. What will happen? And normally it might look something like this. Yeah. But now we have your lambda to infinity. What could it look like? Anyone has any suggestions as to how it will look like?
Your horizontal line then.
Yeah. So a horizontal line probably bisecting your sample space. Because if you have okay, if you look at the loss term, if you have a really large uh, lambda, then you definitely want to minimize this term. And minimizing this term will cause your weight to be approximately 0. And as a result of that, you'll get a horizontal line. Okay, yeah. And that's about it that I want to talk about. So any further questions?
So is this like lambda thing tunable?
Okay, lambda is not usually trainable. Usually you will be setting the lambda, and this lambda is usually actually determined by your optimizer. Yeah. So in somewhere in the optimizer that you use, there's a parameter which usually has something to do with regularization. Yeah. Okay, let's just take a maybe we take like a 10 minutes break for now, and then we come back at 5:20. Meanwhile, just be listening if there's any question.
Teaching, I still don't really understand why this large lambda. What does the lambda have to do with the graph of like the distribution, the frequency?
So your question is regarding how a lambda affects this, is it?
Yeah, yeah.
Okay. So, okay, let's just look at this term again. If you have if the second you introduce something into your loss, right, which is a function you're trying to minimize, what will happen is that your learning algorithm is going to try to minimize whatever term is inside the loss function. So it will try to minimize this, and it wants to minimize the second term. And to minimize the second term here, the only thing you can really change is your weights, right? So to minimize that, you'll want your weights, which normally might look something like 1.2, 3.2, something like that, to go to something that's more like negative 1.0 or like 1.2. So that's closer to 0, right? And because of this, you would expect a average loss value, weight value, to be closer to the 0, right? Because now you're trying to minimize the value of the weights as well. So you realize you expect more of your weights to adopt a 0 value, and but still have some of the weights that's evenly distributed at size, so that they can cancel each other out. So overall, you still get a norm that's close to the 0. That is for the case of a really large lambda, right? So with a really strong regularizing force, more of your weights tends towards 0. But normally speaking, if you do not have a really large lambda, you would expect just a little bit of your weights to be near the 0, or even like just a flat distribution, like uniformly distributed across all these values.
If we want to minimize this term, why at the first place we are add this term into our new loss function?
Okay, so this regularization term is actually trying to essentially prevent your weights from going away from 0, right? So because if your learning algorithm based on the original loss is trying to pick up some specific features within the dataset that does not necessarily have a huge contribution to the loss minimization, then this term will prevent it from trying to learn that feature. Because if the magnitude of this term is larger than whatever little change that learning that little feature will cause you to have, this will cancel it out. So instead, you'll focus on this term more than trying to learn a feature that's potentially a noise. Yeah.
Okay. Yeah, thanks.
Yeah, again, these stuff will we'll have another copy for you guys and probably send it to you all on the chat or something. Or else they might want to compile into something. Yeah. Okay, let's now move on to talking about TensorFlow. I'm gonna change the screen here. Can you guys see this? See this clearly? Sorry, can you just quickly test if you can see what I wrote? Hello? Can you all see what I wrote?
No, I do not speak with gay man.
Okay, so
Yes.
that's yes, good. Okay, so we're good. All right. So just now we covered all the theoretical grounds that you need to know to uh, perform linear regression. Now we need to have some technical knowledge how to use TensorFlow for some of the operations that might be involved. Right. So we'll start from the basics. First, how we make a TF variable. So let's make a x. You can just call TF dot variable. And in this case, let's make this floating point 1 our variable. Okay, now it's stuck. Okay, there. And that should give us 1.0. That's our variable, and we can make another variable that is from a like a list. So instead of one dimensional, instead of just one number, it can be something like 1 2, and it will be list numbers instead. Okay, now you can also sometimes sometimes you might want to control the data type of the variable. So you can see in both cases here, they are float 32, right? So that's one data type. But let's say you want a variable that's like a somewhat different data type. So you have one. I'm not sure if this will work actually. Let's see. Let's say I want a integer instead. Tf dot int. Let's see. 4. Okay, give me error. That's great. Then let's say 1 2, and then we try to make this. So by default, this will probably give you integer. Okay, and in this case, we just turn these apparently integer values into floating points. Okay, so sometimes you might want to specify the the type of data type you want to store in your variable, and it's done by just writing this. So it can be tf.int64 or float32 and so on, right? You can also make constants. So let's say C. Okay, so constant does not have a capitalization, but variable does, and that matters. So and that will be a constant, right? So sometimes you might use constant to store stuff like the lambda we just talked about. We can store something like learning rate, right? So those are constants. And you can also access the shapes of the variable. So for example, we can print, okay, we don't need to print here. We can have, so we declared y just now, which is a list of variables, a list of numbers. You can access the shape of tensor just by typing dot shape, and it'll give you that tensor shape is 2, right? And there's also this concept of ranks. So I can check the rank of tensors by typing tf.rank, and for just a single number, your rank will be 0, right? But if it's, let's say, y, which is a list, the rank will be 1. So if you go to a 2D array, the rank will be 2, and so on and so forth. Right? And you'll notice that TensorFlow calls these things tensors, and tensors are basically arrays which can have really high dimensionalities. So you can go beyond 3 dimensions, you can go into 5 dimensions, so on. So those are generally called tensors. And there's a mathematically more rigorous way to define them, but it's more complicated, and we shouldn't really talk about it. Okay. So sometimes you might be working with data sets that come in the form of Python lists, right? So for example, your X can be something like a list. That's 1, 2, 3, 4. So that's definitely not tensor. That's just a normal Python list, and you still want to perform TensorFlow operations on that. So you have to make this into a variable, sort of. So let's say if it's a variable, you can just make it a variable by passing into this, and dx will be a TensorFlow variable. Okay, and you can also, if you don't want variable, you want tensor, you can just convert tf.convert to tensor and convert x to tensor, and tx is a tensor now. Right, so these two are kind of useful sometimes when you're processing different types of data sets. Okay. And also another thing is that many times you're working with so there are times where you will work with matrix multiplication between the inputs and the weights, and you sort of need a way to initialize your weights. And that brings out the general problem of how can you create stuff like just a random tensor with a certain shape and fill it with random values and so on. So I'm going to talk about some methods that you can use to create lists and fill them up with values, right? So let's say we have weight w, and you want to make it into a TensorFlow variable. And normally, one way of instantiating weights, initializing weights, is to take the weight values from some sort of random distribution. So you can call tf.random.uniform .normal. This will give you a normal distribution, and inside this you'll pass in firstly the shape. Let's say your weight is just 3 by 3, and then you can specify the mean of all the values, and also standard deviation. So these are by default, mean is by default 0, and standard deviation is by default 1. And this will give you a sort of randomly selected values for your weights, and they will have a mean of 0 and a standard deviation of 1. You can also pick your W from, okay, we can just make it into a variable again. You can just call tf.random normal your function the same, it will just return tensor instead. Okay, we can pick from a uniform distribution. And again, we're going to do 3 by 3. And in this case, you'll specify a minimum value. So let's go from 0 to max value of...
Your uniform spelled wrongly, by the way.
Oh, yes. Very good. Something from this to that. Okay, that should be okay. And W will be a uniform distribution now. Yeah. So there's other also ways to pick random values. You can look under random yourself. And sometimes you might also initialize tensor based on a step values. So like 1, and then you go 3, and then you go 5, and so on. TensorFlow also has built-in functions for that. So let's say, okay, let's just do variable again. You can do tf.range, and you give a starting value, start from 0, and our end value, our limit 20, and you can delta, so which is how big a steps you will take, and do delta of 0.5, for example. W will be intervals of 0.5, so it goes from 0 to 0.5 to 1, 1.5, and so on. So this is also a useful function. And sometimes you also need to create just sort of placeholder tensors, which have 0 values or no values and so on. One way of doing that is you can call tf.zeros, and you just need to pass in the shape that you want. Right, so maybe 3 by 3 by 3 or something like that. And W will be just zeros, right? And there's also tf.ones. And again, you pass in the shape, say 3 by 3, and W will be just ones. Okay, so there are these functions. There are many, many more. You can find out yourself, but these are some of the more commonly used ones. So now we know how to create these tensors. We can talk about how we can perform operations. So let's just make something that we can use to perform operations on. Okay, let's make this into a variable, and you can, let's say if you want to add like 1 to this, you can just perform addition normally, but you'll realize that x, after you perform this computation, it becomes a tensor instead of a variable, and that might have some implications as to how your function functions. So instead of doing this, you might want to say x. Okay, make this back into a variable. You can convert, actually, just convert the x into a variable, and x will be back to a variable. Or if you don't want to do the conversion, you can also do x dot assign add. Okay, we add another 1 to it. So now it'll be 3, and you would notice that it's still a variable. Okay, but generally both methods are fine. It depends on what you're exactly doing. And you can also, because most of the time you're not working with just a single number in your tensor, right? So it's more likely that you'll be working with inputs that's higher dimensional tensors. So let's say you have TF.1s, and you have a 4x4. And if you want to add, let's say, 1 to all of these, you can actually just that is interesting. Oh, okay. Yeah, so x dot assign add must have the same values, like the same shape. So you can passing x itself, then you'll be adding itself. So it must have the same shape. Yeah. And if you, let's get, okay, actually we can just use this back. If you perform the normal addition, it actually does not need to be of the same shape. So you realize that element wise is increment by 3, right? So just performing this doesn't need to have the input to be the same shapes. So sometimes you might want to prefer this over assign add. And again, you can convert this back into a variable if you just type tf.variable x, and then it's back into a, okay, now it's what? Oh yeah, tf.variable puts you back into a variable. So that's fine. And what is actually happening here that allows you to directly add 3 to all of the elements is actually sort of broadcasting. So it will, TensorFlow automatically takes the value 3 and make it into the same shape of array as a 4x4 array as the input, as the one you're trying to add to. So then it will have compatible shapes and it can be added together. So you can also manually perform that. So okay, let me just check what's my, okay, so x is this, and let's say you want to add like 256 onto your x, and just make x into a tf variable. And you can actually, so again, if you want to use assign add, it doesn't work, right? Because a needs to be the same shape as x. So what you can do is that you can broadcast this. And you pass in the one you want to broadcast. You want to broadcast a, and you specify the shape that you want to broadcast to. So in this case, x.shape, because we're adding it to x. And you can then x.assign add a, and then that will give you the answer. So broadcasting, and instead of just addition, sometimes you also want to perform stuff like element-wise multiplication, or maybe even matrix multiplication. So let's try a bit of that. Let's make another variable, 1 and 2. Three and 4. Okay. So if you want to element-wise multiply this two together, so the output should be 3, 8. You can simply do x multiplied by y, and then it will automatically just multiply element-wise, so it give you 3, 8. And that's, yeah. So element-wise multiplication is really simple. You can just, yeah, I can keep doing this, and sometimes you have to do cross products. So you have, actually already showed you during that setup session, but we'll just do it again. Let's say I have a more sort of complicated x that's like 1, 2, and 1, 2. So this is a 2 by 2, and we have a y, which is something like, say, that's 3 by 2 by 3 instead. 3, and 1, 2, 3. So x is 2 by 2 and y is 2 by 3. And you know that, say xy can do x dot map xy. So this will perform the matrix multiplication, and do remember that this whatever inner dimension has to match. So 2 has to match with 2 here, and that will allow you to perform the matrix multiplication, which gives output like that. And if you want to put y at the front, you will have to transpose y so that it becomes 3 by 2 instead of 2 by 3. So you can tf dot transpose y and x, and your yx will be like that. So yeah, that. And you can also, if you are too lazy to write matmul, you can perform the same set of operation using this operator, add operator. So x at y would just be the matrix multiplication between x and y, so you see the output is the same. Right. Now the next part is a bit confusing, can be a bit confusing, because when you perform matrix multiplication, it's generally between like lower dimensional tensors, right? So these two-dimensional arrays, then you can do a matrix multiplication pretty easily. But generally, when you're performing machine learning, you like sort of like convolutions, you'll be working with really high dimensional weights and inputs, right? So for example, your image, let's say you have a really small image. Your image itself can have 3 dimensions. I just initialize this randomly. Choose uniform. Okay, let's say our image is 3 by 3 and has a channel depth of 3 because it has RGB channels, right? So it's 3-dimensional. And because it's uniform distribution, so I'm going to give a minimal value. So pixel values range from a minimum value of 0 to a maximum value of, is it 255 or 256? I forgot. Doesn't matter. I think it's 255. All right, and then this should work. Okay, so image is that like that, and you will be performing, let's say, convolutions. Then your kernels will look something like, okay, so this is randomly initialized, so you get a normal. And your kernel, let's say you have a 3 by 3 kernel, and your kernel will also have to match the input depth. So in this case, 3, and you also generally have a certain number of kernels. So common number is 64. So you have 64 3 by 3 by 3 kernels, right? And yeah, the minimum and stuff. So your kernels will look something like this. Oh, squeeze 65 line, yeah, too long. Okay, so it isn't immediately obvious how you will perform this operation between kernel and the image, right? Because they're so high dimensional. Your kernel is 4 dimensions, your image is 3 dimensions, and you can't really use matrix multiplication. So TensorFlow provides a function, or rather NumPy provides a function which TensorFlow adapted, called TensorDot, which is very behaves in very weird fashions, but you don't really have to understand it now. It's very hard to explain as well. So if you want to perform a kernel modification between the image and the kernel, you can perform it on axis 3, which means that it will sort of remove the first 3 axes of both vectors. So image will have a nothing, and then kernels will have nothing. Your end output will be 64 values. Okay, so you can think of it that way. So you sum all the results on the front 3 axes to give you just 64 in the end. So if you perform TensorDot on image and kernels, okay, yeah, and then you'll get output value of you'll get 64 output values, which is the correct shape. So TensorDot is generally used for computations between 2 very high dimensional tensors, and you don't necessarily have to use this because we probably won't be asking you guys to implement convolutions by hand. So yeah, just know that this thing is out there. Okay, so now one thing you have to know is how to perform differentiation. because you have to perform gradient descent, and gradient descent is to use chain rule, and chain rule is based on differentiation. So it's kind of important to know how to do differentiations. So let's talk about that. Let's have some input value x, make it into a tf variable. It's very important that your values that you're trying to differentiate is tf variable. Say 1.23, and let's say you have, okay, let's do a linear one, right? So you have a weight of, say, 0.5, and you have an offset, which is a bias, 0.5 as well. Okay, so TensorFlow actually has built-in auto differentiation methods, so you don't have to manually go and compute the differentiation of expressions. So what you do is you instantiate a gradient tape. Let's call it tape. And inside here, you can perform your whatever operation. So y equals to x multiplied w plus c, so that's your linear operation. And once you perform that within the gradient tape, outside of the tape, you can compute the different. You can differentiate this expression. So, for example, if you want to find dy dw, you get a tape and you gradient it. And you put in the value you want to like differentiate with in respect to w. So then dy dw will give you 1.23, which is correct, right? So that's how you perform differentiation in TensorFlow. There's a few quirks of this. For example, now if I try to, now that I've performed this differentiation once, I want to find dy db, because wait, actually, okay, this is actually performed wrongly. Okay, but whatever. If you let's say I want to find the grade dy dc. Okay, if I type dy dc equals to tape of gradient y and c, you realize it will throw you an error because this tape can only differentiate stuff once, right? So you can only perform one differentiation, and after you perform this differentiation, this tape is gone. You can't use it anymore. Okay, so there's a few ways to go around this. The first way is that you just find the gradient. You perform all these differentiation at the same time. So let's do the gradient tape again. Okay, this time correctly. Y equals to mw multiplied by x plus b, right? So if you want dy db and dy dw, you can actually perform this differentiation for both values at the same time. Okay, y, and then you put in a list of variables you want to differentiate in respect to. In this case, we want to differentiate with respect to w and b. And if you get dw, it'll be this, and b should be 1. Yes. So that's one way of going around that thing. The other way, as the error is suggesting, you can set the persistence, the gradient tape to be persistent. So what I mean by that, let's just make some new values. Whatever, and w equals to. Okay, I don't know why I'm doing this. But just make it this. BP. And okay, gradient tape as usual. Now you can pass in an argument here. This is persistent equals to true. So now your gradient tape is persistent. And we perform the same set of operations. TensorFlow has no gradient. Oh, okay, that's spelled wrongly. Do it again. Y equals x. Oh my god. Okay. I think it's type mismatch. Okay, I have to redeclare them. Okay. Okay, that should be fine. And now we can actually perform the differentiation separately. Y with respect to W and dy dv. Y with respect to the okay. Tape. Right, so it will work because you set persistent equals true. Okay, so those are two ways to go around that weird error there. And now let's talk about operating, trying to compute gradient on tensors. I stress that you must use variables for this to work, because it must be variable for that to work. So if your weight is, for example, like some tensor instead of a variable, and now you try to compute the gradient, so everything is the same except now your W is a tensor, and now you try to find dy dw. You realize that the gradient output is nothing, is none. So you have to keep in mind, whenever you try to use the gradient tape, that you want to make sure your whatever stuff you're trying to differentiate and your variables should be TF variable instead of tensors. Or another way to circumvent that is, instead of just performing this normally, you will have the tape watch for the value that you are differentiating with respect to. So in this case, our W is still a tensor. Now I watch for W, and you perform the same set of operations. Now I compute the gradient. Now it wouldn't be none because you watched for the value. So you either watch for the value that you want to differentiate to in respect to, or you just make sure that all your values are tensors. Okay. And yeah, we have only been doing this for like really simple case where it's just single values. You can also perform this differentiation when you're working with high dimensional tensors. So let's take the example of that convolution filters that we were doing. So let's get some image that's 3 by 3 by 3. Let's get some weights. This is 3 by 3 by. See, we have 64 filters. And you have a bias of shape 1 by 64. So each filter has its own bias, and you try to use gradient tape. And now you perform that same tensor dot operation. So correct, and x, w from the third axis, and you plot the bias. And now you want to find the gradient. Y with respect to W and B. And let's print this huge thing out. This is too big, so that you will, yeah. So what happens is that for every single one of the weights inside this variable, it will get its own gradient, so you can update them individually. Yeah. And the bias similarly will also have something like that. In this case, everything is 1. Yeah. So yeah, that's about all that I want to cover. And this should actually prepare you guys for the first project, which we're probably going to ask you guys to implement your own linear regression model. A very simple task, and you'll probably make use of basically everything I've said here. We'll also be sending a collab notebook that has all of these little bits that we talk about throughout this entire session here, and you guys can refer to that if you're not clear about any of these concepts. So for now, is there any question?
Is there any Google Doc where we can find all of this?
Yeah, I think Alice will compile one, or at least I will send you all everything I've talked about this. And if in any case you're not clear about anything regarding TensorFlow, you can just look at their official documentation. Yeah, they have samples and everything. But everything we talked about here today is compiled into a collab notebook, and we'll give you access to it. Any other questions? You all do understand what everything I covered, right? It wasn't too difficult, right?
I'm not completely sure what TensorDot does.
Oh yeah, nobody's sure what TensorDot does. Even I can't really explain what TensorDot does. Zari, can you explain what TensorDot does?
Takes two tensors and dot it along a specified axis. Yes.
Yeah, so basically
More
it's very
details can be
counterintuitive.
found on the TensorFlow documentation.
Nah, you won't be able to understand it. To understand TensorDot, you probably have to sit through some 12 video math course to get what TensorDot is doing. But at least what I've told you about the axes is correct. So you will basically take away the axes, like, and then sort of you just go by that to get the correct output shape. And if the output shape is correct, your input is your operation is probably correct. You can find out more. You can read up about it yourself, but you probably won't be using this because I've been doing machine learning for like since like Sec 2 and I've never used that shit until now. So it's fine. If there are no question, you can leave. We'll probably write a little doc regarding the linear regression project thing that I was talking about and send in the chat. Then you guys can work on it. Yeah, shouldn't take too long. It should take maybe like 1 hour, maybe, I don't know. If you have no questions, you can leave. If you're staying, then you better ask questions.
以前 yeah, I want to ask right,
Mm-hmm,
like just now you introduced like the weights times the B thingy, right?
Yeah,
Like
yeah.
in like okay, like in real application, right, do we like use by that or do we use like the keras layer stuff?
In when you're making your own model, it's probably gonna use Keras layers, but we'll try to at least get you to implement linear regression from scratch, so at least you know the process.
Okay, can.
Yeah. But generally, you don't have to worry
You.
about that. Yeah.
Wait, so generally if we do like keras layer stuff, we just do like know like the input numpy array and then the output stuff, right? Like don't need to know like the like the tf dot variable stuff.
Okay. So if you're only dabbling with the pre-implemented stuff, yeah, that's enough. But most of the time, as you get more and more advanced, you probably will have to customize your own layers. So you probably have some custom conv layers, and with that, you'll have to dabble with gradient tape. You'll have to dabble with the variables and stuff. Yeah.
Oh, okay, thank you.
Yeah. Why are people still staying here? Are they sleeping and just forgot to leave? Zari, have you ended the recording? Zari,
Nah, still recording.
you can stop recording now.